Hello community! You are not gonna believe it, we have an explanation why grokking is happening. Look at this, finally! And yeah, I'm not talking here about your particular company who called the marketing name of their models grok or anything like it. I'm talking here about the technology phenomenon that we have in our transformer architecture. So purely technical, that happens with every transformer. So 7 months ago, my goodness, I've shown you here multiple videos where we examine grokking. Grokking is that if you have your accuracy and you have your training data set saturates, you have overfitting of your LLM, but then nothing happens and you have a real bad performance on your validation data set. But you know what? If you just let it run and run and run, long after the overfitting of the training set sets in, suddenly there's a performance increase and our validation dataset accuracy goes up to almost 100%. And this is great. If you could achieve this immediately, imagine we would have a system that is for unseen training data achieving close to 100%. And in this video, part 3, I showed you here the grokked LLM versus direct system, how we can optimize this. And we even had a deep dive into the layer architecture when the retrieval heads in our AI agents were discovered. And we had here causal computation pathways after the grokking happens. But we never could explain why grokking happens in the first place or how we could ignite it earlier. And now today we have new research into grokking, and this is beautiful. So let me give you now finally the reason why grokking happens late and suddenly, because our LLM first gets trapped into a lazy training regime where the memorization effect is the dominant force of learning. Then the system gradients align here with a particular direction I'm going to explain in a minute. This has the effect that we scale now the logits from every layer to the extremes, which in turn leads here to the perfect softmax collapse. This means our layers and our LLMs encounter a numerical instability phase, stopping each and every meaningful learning process of the LLM. Now, if you are not immediately familiar and understand 100% of this, hey, this video is for you. So let's start, because it took also some time to understand really what is the root cause of this. I really want to go here that everybody is able to understand why grokking is happening and how you can achieve finally close to 100% performance of your LLM. It all starts here with the numbers that we use in our calculation. So we use floating point numbers, and they have a certain name of significant bits which define the precision which we do here, the matrix multiplication or the tensor computation. And the concept of a significant or a mantissa is here in a scientific notation, of course, and you can use any base, not just the base 10. We in binary have the base 2 or whatever base you like to go with. So in general, we have our number, and this is the way we can build it. Our significant, our base, and the exponent. Here's everything explained for you. But let's have here a real example here. So counting now the significant digit in a significand. Key to remember is that the significand in its normalized forms includes here the digits before the decimal points, always a non-zero digit in most representations, simply assumed to be 1 in the binary floating point format, and it is not stored explicitly. And then we have the digit after decimal points, which are part of the representation. Really easy example, 1234.56. We can have this in a scientific notation like this, and you see the significand has 6 significant digits. 1, 2, 3, 4, 5, 6. Look at the next example. This is here a beautiful number, and the significand has 9 significant digits. However, we can write this in a scientific notation in this form. And now you already have a clue what's going to happen. Yeah? If the limited significand has, for example, only 6 digits, we are limited simply by the precision in which we do our mathematical calculations. Because, I just showed you here, we have with this number 9 significant digits. But let's say we only go with 6 digits. so 6 significant digits, then this would be approximately and stored in our calculation as this number. So we lose information. Now, if you have a look at the base 10 representation of this, let's go to the extreme. And let's have here, look, this is here the base value if you want. And then we have here this particular value for the correction, for the gradients. If we calculate here our gradient descent, if we calculate backpropagation, we have to do all of these calculations. If you not see it immediately, look, this is the same number like this one, and this here is the same number like this one. And now we just add those two numbers, and you say, of course, this is it. Yeah, but imagine we only calculate with 6 significant digits. And I have shown you here in green the 6 significant digits. So you see, absolutely, given now the mathematical precision in which we calculate our mathematical tensor calculation, we lose information. So due to the small number of digits for the significant, which is 6 in this case, the result now is not this correct mathematical results, but now stored in our LLM, done by mathematics, the result is now this, only with our 6 significant digits. And yes, you guessed it, this is the root cause why we have here, after you reach a 100% overfitting of your training data, why the system collapses. Let's have a look at this in detail. It is so important, and I will again repeat this. They have here a new notation, what they call a softmax collapse in the neural network in the transformer layers. So let's have, task is simple, we have a problem, you just identify 3 classes. And we are working here with float 32, which have 24 bits of the significant. So the logit here for our simple 3-class identification have now a particular samples, and let's say they are -10, -5, and 20. And you can clearly see 20 is here the dominant number. Yeah? Now the softmax function would normalize now these exponentiated values into a probability distribution. So what we get here from our logit, if we do simply the softmax calculation, we would get this. And you say, yeah, that's absolutely fine. No, this is insignificant, and this is it. Yeah, but wait. We calculate the loss function. And the loss function gives us here our gradient. So the loss for this simple example with the assumption that the class 3, our 20, our dominant class, our dominant value is here, the true class, would be really small, approaching 0. And if we calculate now the loss function here, we see that our gradient goes to 0. And you might say, yeah, and? Let me repeat this. Our gradient goes to 0. This means the system is stuck. The system doesn't move anymore. Because if there is not a gradient in a gravitational potential, the system does not know how to further optimize the equations. Because the gradient is 0. And 0 is stop. And this is the reason why we have this long period of 100% training data overfitting, but not learning. Another time, real example, floating point calculations. Again, we go with a precision of float 32. So a 32 24-bit significant calculation. Let's take this, let's go with this -10, this -5, and 20. Now, let's calculate x of 10 and x of -5. They're real small numbers. I've given you a little bit more mathematical precision. Those are the numbers here. And then we have our dominant factor, x20. And this is 485,165,195, 409, and whatever. So what we do now, you remember, when we calculate now softmax, what we do, in the denominator we have a summation function over the exponent here of our z's, of our, logits. So this is exactly what we did. These are now the exponential values of our z's. So we sum over that, and then softmax is exactly, and this is here exactly what we divide. And now you say softmax is this, no? No problem. again, we are looking here, the dominant factor is here the entropy loss, the cross entropy loss function. This is what gives us here the direction for the development of the system. So if the softmax output becomes close to 0.001, so the output is a valid probability distribution. This is why we do softmax. And this cross entropy loss for the correctly classified samples approaches 0. So this means the gradient now of our cross entropy loss function with respect to the weights is 0, is standstill, is inactivity, is dead. And this is what we do not want to happen if we are not even in a local minimum. If you are not really just softmax function transform here a vector of logits, this means our unnormalized score Z into a probability distribution. This is why we do softmax. Simple formula. And crucially, this new research now demonstrates that during the training phase, after reaching our 100% training accuracy, not evaluation, the training accuracy of the data set of the training, the model tends to increase now the magnitude of the logits, particular for the correct class. And you say, what? And I said, what does this mean? You tell me that the loss function continues to optimize here itself for a system configuration that is not inducing any new learning? Exactly. You know what it does? It only increases the magnitude of our logits Z. I want to bring this point over because this is so important. So when the logits become very large, they can cause the gradients from a large fraction of the sample to become 0, effectively stopping the learning process and preventing here the LLM to be able to generalization of knowledge to unseen data. So this is the core mechanism that the new research paper identifies as softmax collapse. And this is a crucial element in understanding grokking, because this happens before grokking takes place, and this happens while our LLMs do not reach 100%. Simple here potential, x and y axis, and let's say this is here the absolute minimum, and this would be here our potential form, and we are here with our optimization of the loss function, and here suddenly our gradient becomes 0, so there's no direction to go. All the complete entropy loss optimization that we have in our LLM to learn new knowledge converges to 0. So we stay here. We don't learn anything new. We are trapped. So this softmax collapse is now a key obstacle to the generalization of knowledge, and that overcoming it is now the major step that allowing grokking to happen. So interesting, before grokking, we have a numerical mathematical instability in our transformer calculations. And investigating now the root cause of this softmax collapse, the authors found beyond the point of overfitting, the gradients strongly align now with what they call here a particular minimization direction on the potential well, and they call this here the naive loss minimization direction, the NLMD. Why is this problematic? Again, the model reduces the loss not through the learning a more meaningful representation, but by scaling the logits. And I will again explain what scaling the logit really means, but the effect is that it delays the generalization of the knowledge and leads here to complete system-wide numeric instability. This means that scaling of the logic explains the delay in the generalization characteristics of grokking and why the learning stops of our LLM. So let's have a look at this. Scaling of the logit refers to a specific type of transformation applied to the logic vector Z, where the individual components are multiplied by a constant. And the new research identifies that the update of the network weights have a particular mathematical effect that is equally of changing the logits via a constant value C. This is it. This is what you have to wrap your mind around and say, why? So the answer is that the scaling factor C is applied to each element of the logic vector Z individually. And researchers argue that after the model achieves the 100% training set accuracy, the gradient updates begins to align with what they call the naive loss minimization direction. And if you want, a simple mathematical formulation is here. And we have here the scaling with a factor with a constant C. So our logits Z are now simply scaled with this factor. Now this particular LLM direction in a mathematical space corresponds now to parameter updates in a specific way that have the effect of scaling the logic, meaning the updates are such that if we take it a complete function, it results simply here in a multiplicative factor. Again, this formula here states that applying an update to the model parameters in the direction specified here by the change is equivalent to scaling the original output of the neural network by a positive constant. So nothing is learned. This D here is a specific direction in the parameter space that the new research identifies as the naive loss minimization direction. It's a parameter update that the gradients start to favor after the training data is correctly classified, because it decreases the loss at the expense of increasing here the softmax function. So the update is dependent on the current parameter state phi, and the function f represents here the complete neural network function. It's a complex mathematical function parameterized by theta that takes an input x and produces the output logit z before applying here the softmax functions. So when we scale the logit by a constant factor c greater than 1, the probabilities will be increased for the correct class. So interestingly, the softmax for the correct class gets closer to 1 and the cross entropy loss function gets lower. Look. So when they call this NLM a naive form of an optimization, you immediately understand why. Because the model is not anymore improving its ability to learn to differentiate between the three class problems. Instead, the optimization methodology is now in a naive function, if you want, simply scaling all of its output value to further decrease its loss. But this makes no sense. This is just a mathematical operation to reduce the loss without any learning function. So if you think about here Z1, Z2, and Z3 that I showed you in an example, this is achieved by scaling all the weights along the current direction, x, y, z, which has the effect of scaling the logits. Therefore, what's happening now after this 100% overfitting is just a wrong form of optimization, a naive form of optimization that is just a mathematical trick to make the number bigger, but you do not enable the learning to happen with a loss function. This is the beautiful paper we have here at Department of Computing, Imperial College of London, Grokking at the edge of numerical stability. Before we get a numerical instability in our transformer network, published January 8, 2025, beautiful. I have a GitHub code, everything is there for you. And they show that the software collapse prevents here the onset of the grokking, and that mitigating here the software collapse leads to grokking even without regularization. Give me 5 minutes and I explain this in detail. So, investigating now the root cause of this SC, the authors say, we find that beyond the point of overfitting, the gradient strongly aligns with what we call the naive loss minimization direction, and therefore no learning is happening in the system. If you want to see this in a formula, it's really easy to read. I mean, this is how I read the paper before I made here this simplified explanation in this video for you. So here you have the softmax cross entropy loss. Here you have the softmax collapse described here. The SCE loss becomes 0, exactly as we said. This is the softmax collapse. And the naive loss minimalization, if you do here this function, you see exactly here that the function here of the neural network here is more or less equivalent to multiplying this with a constant factor c. So this is now interesting. So the whole learning process that is based on the entropy loss optimization of this loss function is now just a scaling functionality, but not a learning functionality. And there's more. And they say, we find that under a large class of models, to what transform architecture does it apply? Namely those that demonstrate here a positive homogeneity. When training beyond 100% training accuracy, the direction of the weight is indeed an LLM direction. And they have here this definition of this positive homogeneity function here, where exactly this formula applies. L corresponds to the number of layers. And they say many neural network architectures, such as the ReLU MLPs and the transform architecture without bias terms, are indeed positively homogeneous or approximately homogeneous in the case of the transformer network. If you want to learn more about this, I would recommend you this paper. It's an old paper, but it's a brilliant paper from Tsinghua University. This is from end of December 2020. This is version 4 already. And it's about gradient descent maximization, the margin of homogeneous neural network, and they study implicit regularization of the gradient descent algorithm. So if you want to have a mathematical deep dive, I love this paper. Great. So what happens? After the LLM reaches now here the 100% training dataset accuracy, the LLM dynamic pushes the model to scale only its logit by scaling the weights. So this indeed reduces the loss in the cross entropy, but at the expense of learning meaningful representation, increasing the magnitude of the weights, increasing the numerical instability of the softmax, and finally leading to the softmax collapse. So here we have the model is now trapped by this particular training dynamics. This optimization here of the loss function served us so well for so many years. But there's also the dark side to this. It can trap our model and prevent further learning and prevent further grokking. Interestingly, if you read the literature, they found some interesting points. And the author said we investigate that by decreasing the dimensionality of the input, the data becomes harder to memorize for the LLM, thereby removing the delay in the generalization onset with grokking. So this is now fascinating. This is the next hint what we have to do to achieve grokking much earlier on. They say this confirms our hypothesis that showing as the input representations are decreased in the dimension, overfitting is prevented by our LLMs, and our LLMs generalize earlier and the grokking phase is earlier. And this is exactly what we wanted. However, in our complex multi-jump reasoning architecture of real complex problems, we don't want here to decrease the dimensionality of the input because we need the complexity to really span here the input space, if you want. But this gives us a hint what we have to do. And you're not going to believe it. Having these insights, now the author come up with 2 new ideas. So we need, and they develop a mechanism to escape this trap, to start learning again a real meaningful representation that allows for a really excellent generalization of up to 100% accuracy on the dev dataset. Isn't this beautiful? I had to wait 7 months to finally understand what is happening before grokking and why grokking is delayed so much. So now we are in the position to say, okay, I understand what's happening here, and now I understand what is happening here now. And now, understanding this, you know what we're going to do? We're going to bring here the onset of grokking real close here to the beginning so that we do not have to waste our time for thousands and thousands and 10,000 more optimization steps, or we don't have to waste the energy, we don't have to waste the time, we don't have to waste whatever computation. We can build now our grokking LLMs much earlier onset And I can tell you, I have two systems that I grokked here in the old times, and I hold on to these two grokked LLMs here like it's the, I don't know, the crown jewels here of the British Empire, because those systems have a performance that is simply, an accuracy that is simply amazing. So this opens up now complete new avenues to improve it. But of course, this will be then the content of the video of tomorrow. I hope you enjoyed here the introduction to grokking, the first explanation why grokking happens, what is a softmax collapse, and yeah, I can think now of 4 methods to overcome these probabilities, to circumvent here the numerical instability. But you know what? There's another interesting question that I have to run some tests now. They are, of course, if people do not have the computer infrastructure, they go down to an 8-bit quantization of the LLMs. And now the main question is it possible to do the quantization in a way, in a form, that we can ignite grokking earlier? This is done and is shown here by the researcher here for a floating point 16. But if we do simplification by quantization of our models, and now it depends heavily how we quantize it, what value we quantize, at what stage in the training we set in our quantization models. So I think this is now absolutely fascinating. If you want to bring this down to smaller models, small language model, how we can cope with this early onset of grokking to reach a 100% performance. I mean, this would be amazing, but let's do the first step now. Part 2 is coming up, and I show you multiple solutions, how we can improve and have immediately grokking, immediately an amazing performance for our LLM. I hope you enjoyed it, and if you are a subscriber of my channel, you will get immediately notified when part 2 becomes available.